Hello everyone, this video tutorial is about axisymmetric problem analysis in Abaqus. So here is an axisymmetric problem. It was taken from chapter 10 of Introduction to Finite Element Analysis using MATLAB and Abaqus. That's chapter 10, Axisymmetric Problems, and that's the solved problem. So here, this is a circular footing of a sandy soil. So the statement is this figure on left side, yellow figure, represent a circular footing on a sandy soil with an elastic modulus 10 to raise per 5 kilonewton per meter square, a Poisson's ratio of 0.3. The footing is 2 meter in radius. That footing is 2 meter in radius and supports a load of 200 kilonewton. So 9 meter beneath the footing, the soil is made up of a solid rock formation that can be considered very stiff. So, so that is a problem. And here we have axisymmetric problems. So like as this is for just for explanation that what the axisymmetric problems are. So that is a circular annulus and then some load is being applied. So when we have to solve this type of problems, so instead of modeling whole of the problem, so we just take a strip out of it. So like this one, it is the thick walled annulus that's shown there has internal radius of 400 millimeter, external radius of 7, and then it is subjected to top surface of load of 0.5 Newton per millimeter and a line load and a base is 4 Newton. So that is basically an annulus, and this is this is symmetric. This one is symmetric about its axis. So what is the usual procedure in FEA or in a commercial software like Abaqus to solve this type of problem? So instead of modeling the whole of it, we just take out an element out of it. So that element here, when it is taken like, so it has uh, height and then its width, so that a section has been taken and it can be modeled as a like simple plate, or it can be modeled as a simple plate. So similarly, the problem which is here, so this one, this whole stuff is in circular form. So, and it is symmetric about this axis, which is being shown like as a center line. So if one side is being taken, and when the one side is being taken, so here it is, this one is that is symmetric about that y-axis shown here. So that is axis of symmetry. And when it's being axis of symmetry, so here the boundary conditions are x-symmetricals. And then again here they are x-symmetrical and the foundation is just pin support. Now this 200 kilonewton load, it can be converted into pressure, and that 200 kilonewton divided by area, which is pi into 1 squared. So you will get that load converted into pressure. So the problem with the green background, it can be modeled in Abaqus as an axisymmetric problem. So that's Abaqus, and here are steps to follow in Abaqus. So you need to first use a set of unit, so like Newton meter Pascal or pound inch or and pound per square inch. You need to first set work directory, and work directory I want to save everything in chapter 11. So that is a work directory you need to set. So file, set work directory, and here that is a work directory is being set. And then the first step is create part. So here part, so it is now it is I'm just say that part is footing, and that is axisymmetric deformable shell, and its approximate size is double of that, and it is I'm taking it as 20. Okay, and that you can see that here. Uh, you can see that is symmetric axis. So now this can be modeled as a rectangle with width as 7 and height as 9. So here you can use that connected lines, or you can create rectangle and then it is 7 its width and height as 9. Then cancel procedure, then done. So this is the model, 2D model, axisymmetric model is being created. Now the next step is you need to assign material, and material for that is soil with modulus of elasticity 10 to raise per 5 kilonewton uh, per meter square, and it's going to be 1 into 10 to raise per 8 Newton Pascal. So here in the property module, that is the material. So material is sand. So material is mechanical elasticity and elastic, and Poisson's ratio is 1 into 10 to raise per 8. Modulus of elasticity 1 into 10 to raise per 8, because it's 10 to raise per 5 kilonewton, so it will become 10 to raise per 8 in Pascal. And then the Poisson's ratio is 0.3, which is there. Okay, so now material has been assigned. After that, so the next step is create section, and here you have create section, or you can double click here to create section. So section is solid homogeneous, and let's say I am saying it as section is solid homogeneous, and then material is sand, and you need to uncheck that plane strain stress thickness, because for axisymmetric we are not considering that thickness, so that is okay. So next step is to assign section. So here you have assign section, or you can go into the part here and then section assignment. So it says that select the region to be assigned section. So that is being selected, done, and then that is being section is being created here. So you have assigned section here. So after assigning section, the next step is you need to go into assembly. So here is assembly module, and then create instance. So footing, that is done. And now after that, you need to create step. So step is step 1, okay, and static journal, continue, and that's done. So next is to apply loads and boundary condition. But for load, so load is being applied at 1 meter from that axis. So because we have modeled that is a triangle, so need to create a partition here, and for that one at this end, a partition need to be created, and for that one, you can go to part, or you can go tool first, create a datum point by entering coordinates, and the coordinates of that point are uh, this one is 1 along x-axis and 9 along y-axis. So it is 1, 9, and 0. So that you have there. And then after that, you can see that in the features here, datum point is being created, and it is being created at 1 and 9, 1 along x-axis and 9 along y-axis. And then you can go here, tool, partition, create partition edge. So, and then select datum point. So select an edge to partition, that is edge to partition, and then select a point. So that a point is being selected, and then partition has been created. Now you have that section to apply load. Now the load 200 kilonewton, equivalent is 63.662, and that is the pressure. So here loads, and load is pressure, and then you need to Here select pressure is a step 1. Okay, pressure, continue, select that edge, and then the value is 63.662, 63.662, and then OK. So now you need to create boundary condition. So here you can select that axisymmetric. Here you can also select as axisymmetric. So that is left, right, and that is bottom. So in boundary condition, that is left, and left is symmetric, that is axisymmetric, and then symmetry, antisymmetry, continue, that you need to select this edge, and then it is axisymmetric because it is perpendicular to x-axis, but now because r theta t for axisymmetric problem, but still this edge is perpendicular to x-axis, axisymmetric, that is for left. Then next one is right, and again that is this one, that is symmetric, and that is axisymmetry, and then you can create from here boundary condition, that is bottom, and then step 1 and displacement rotation, continue this one here, so done, and it is a pin support, assumed as a pin support, so u1 and u2 are 0. Okay, so now you have created all boundary conditions. So then one thing is missed there, and that is you need to create mesh. Okay, so here mesh is empty. You can go there and then you can have that seed part. Okay, so and approximate size you can take 1, apply. Okay, so that is approximate size, and even you can reduce it to 0.5 as well, or even a lower one. Okay, and then here that is mesh. Now here you mesh part and now assign element type, and in element type you need to go, this is assign element type, and assign element type is family is axisymmetric stress, so standard, and then you can use quadratic, 8 node by quadratic axisymmetric, 8 node by quadratic axisymmetric quadrilateral, and with the reduced integration, or you can uncheck from there, so it will become CAX8. Okay, or by default it is reduced integration. So then now that part also done, and next you go to analysis, and in analysis you need to create job, then data check and submit. Okay, before that I'm going to save this model as, so rename, so this is from chapter, let's say 10, example. Okay, that, and then I'm going to save that, file save, so that is chapter 10 example. So in the model name or saving that whole CAE file, you can use spaces. Now in the job, it is chapter 10 example, but you can't use here spaces. So continue, leave everything as it is. So now you have it. So then submit for data check. So data check submitted, it will start running, and after some time it will be is completed. So it's completed, it means that necessary steps for this model are done. Then you can submit that job. Okay, so it's submitted, then it will start running, and then it will complete it after some. So that has been completed. So once it's completed, then you can go to the result, visualize the results. So you can right click on that and go to results. And then you can see in our model output database, you have that chapter 10 example ODB. I'm going to close it. There is another way, file open, and you can have here output database. Okay, that you have, and that is now this is for one Mises stresses, and if you want to go for stresses in y direction, if you want to see that what are the stresses in x direction, and then you can have here u1 u1, you'll have there u2, and you can visualize results. So you can go to common plot option, you can apply here node labels that are being applied. Okay, there are so many node labels. So whatever you want from there, so you can create report for any parameter which is required. I hope you like this video. Thank you very much for watching. You can comment for feedback.